Welcome to the first course of quantum mechanics. As I had mentioned in the introductory video posted in Moodle, quantum mechanics is an entirely new thing to you. It is totally different from the classical physics with entirely new concepts and mathematical formulations. In this course of quantum mechanics 1, we will learn mostly the basics of quantum mechanics with simple mathematical tools. Next semester, we will be having a different approach with a more rigorous mathematical treatment. If you grasp the concepts of quantum mechanics in this semester, advanced topics of quantum mechanics in next semester won't be much difficult to understand. So try to understand the concepts of quantum mechanics without fail. In the first module of this course, we will see the failures of classical mechanics to explain certain phenomena like blackbody radiation and photoelectric effect. We will see how energy quantization concept helped scientists to overcome the issues. We will also discuss about wave-particle duality in this module. In this first lecture, we are discussing one of the biggest issues faced by 19th century physicists, the blackbody spectrum. We will see how this issue actually turned out to be a disaster of classical mechanics. Thermal radiation is a quite common thing in the universe. Heated bodies can emit both heat and light. This is basically a single process, and we use the term thermal radiation to all emissions of a body due to a heating process. In 19th century itself, physicists had given qualitative description for thermal radiation. One such law says the more a body is heated, the brighter it glows, and another one states that the color of the emission changes with an increase in temperature. Usually, physicists use some kind of standards to compare the properties of objects. In the case of thermal radiation, since there is a great diversity of bodies and conditions in which thermal radiation is emitted, scientists tried to find out some kind of a standard body which can be used as a basis for establishing the laws of radiation of heated bodies. Then the emission of light by other bodies could be treated as deviations from this standard body. The search for a standard body ended up in black bodies. A black body absorbs almost all radiations falling on it and hence is heated by this radiation to a higher temperature than all other bodies. Conversely, when a black body is heated to a higher temperature, it emits more intensely at the given temperature than any other bodies. Therefore, scientists considered the black body as a convenient radiator for establishing the qualitative laws of thermal radiation. However, black body themselves emit radiation in different ways. For example, soot and black velvet can have quite different radiation spectrum. So, the ideal black body must absorb all radiation falling on it. A blackest body can be imagined a special kind of hollow object with its inner walls coated with the soot and with a tiny hole on its surface. Such an object is shown on the right side of this slide. Any radiation striking on this hole enters into the object and never gets out. That is, it gets caught by the black body for all time and body gets heated up in this process. When the body is heated sufficiently, the walls become incandescent and begins to emit radiations. All laws of thermal radiations were established precisely for this kind of black bodies. With slight alterations, this law apply also to grey bodies. So a typical black body spectrum for different temperatures of emitting body looks like this. Let's now discuss the classical laws associated with the black body emission. The first law states that the radiating capacity of a black body, that is, the energy it emits in the form of light and heat every second, is proportional to the fourth power of its absolute temperature. This law was discovered by German scientist Stefan and Boltzmann, and hence it is known as Stefan Boltzmann's law. The second law states that as the temperature of a black body increases, the wavelength corresponding to maximum brightness of the light emitted by it must become shorter and is shifted towards the violet region of the spectrum. This was called Wien's displacement law. Keep in mind that when a body is heated, its radiation widens the spectral range. As a result, if the temperature gets high enough, we have a complete visible emission spectrum. But Wien's law speaks only about the color corresponding to maximum brightness of light radiation. In addition to this radiation, there can be radiations of different wavelengths. When there are different laws about a same thing, physicists always try to unify them. As soon as it is discovered that one and the same phenomena is described in various aspects by several laws, they will try to combine them into a single general law encompassing all aspects at once. Such an attempt was made with respect to the laws of thermal radiation by the English physicist Lord Rayleigh and James Jeans. According to Rayleigh and Jeans, the density of standing waves in the frequency interval between nu and d nu per unit volume inside the black body cavity is given by g of nu d nu equal to 8 pi nu square by c cube d nu. According to classical equipartition theory, the average energy per standing wave is given by kT. So, the total energy U of nu d nu in the frequency interval between nu and nu plus d nu per unit volume is given by this expression 8 pi kT nu square by c cube into d nu. So this was the unified law. And this unified law stated that the intensity of radiation emitted by a hot body is directly proportional to the absolute temperature and the square of the frequency of the emitted light. This law was in good agreement with observation only for the longer wavelength region or the shorter frequency region as shown by these dotted lines here. The law breaks down towards the shorter wavelength region or the ultraviolet end of the spectrum. According to Rayleigh and Jeans, the higher the frequency, the greater should be the intensity of thermal radiation, and as we move to higher and higher frequency, the radiation intensity was supposed to increase without bounds. As you know, in this universe, nothing exists without bounds except the universe itself. So, if a physical law leads to unboundness, it is a disaster. This situation that arose in the theory of radiation became known as the ultraviolet catastrophe. There was nothing wrong with the Rayleigh and Jeans mathematical formulations. It was the collapse of the entire theory that gave birth to the law, the catastrophe of classical physics. Even though physicists of that time made various attempts to surmount the difficulties of radiation theory, nothing actually helped to overcome the situation. The same years saw the collapse of another well-known theory, the ether model, proposed to explain the constancy of velocity of light. This collapse led many scientists in complete despair and become hopeless. Many even thought that nature is unknowable. However, there were few scientists whose reaction was rationally different. They wanted the theory to be reconstructed on a new basis with immediate effect. A new way to come out of all these troubles of classical physics was found by Max Planck, who in 1900 introduced the concept of quanta, and by Albert Einstein, who in 1905 developed the theory of photoelectric effect. Max Planck was haunted by the idea that two laws separately working very well become a catastrophe when joined. Planck checked the entire chain of reasoning in Rayleigh-Jean's formula and convinced that there was no mistake. Planck was studying thermal radiation for many years and he tried to find some general formula that fits blackbody radiation. After several tries, he finally got a formula which contained expressions that do not have obvious physical meaning. His formula was just an accidental formulation of unrelated quantities. But strangely, this was in excellent agreement with experiment. Moreover, he was able to derive the Stefan Boltzmann's law and the Wien's law from his new formula. But Planck himself was doubtful about his new theory. His formula was not derivable from the laws of classical physics, yet it fit the experimental data in miraculous fashion. I told you that Planck's formula was not possible to derive from the laws of classical physics. Do you know what was that made it impossible to derive Planck's formula? It was the unshakable idea of that time the energy is continuous. Scientists of that time believed that molecules were constantly exchanging energy in every imaginable quantity. Energy of wave motion was also believed to be continuous. Since Maxwell proved that light is electromagnetic waves, energy of light radiation was also thought to be continuous. When the concept of molecule was introduced into science, it was a well accepted fact that there was no such thing as a piece of any material smaller than a molecule of that material. So, discreteness of matter was not a difficult thing to be accepted by physicists. Same time, in the case of energy, there was no such notion of discreteness. Max Planck suggested that, like matter itself, the energy of radiation is atomistic and that it is released and acquired not continuously but in small portions called quanta. Concept of quanta were vitally important for Planck's formula, without which his theory would have failed miserably. These quanta of energy served as a firm foundation for Planck's formula. But the foundation itself rested on practically nothing since there was no place for it in classical physics. A quantum of light is an extremely small portion of energy. We know that even minute particles of dust has thousands of millions of atoms in it. The radiant energy released by a tiny glowing object contains thousands of millions of quanta. Planck discovered that the portion of energy in quanta is different for different types of radiation. The shorter the wavelength of light, the larger the portion of energy in its quanta. Mathematically, it is expressed as E equal to h nu. Here, E is the energy carried by the quantum, and nu is the frequency of the quantum, and h is a proportionality constant which turned out to be same for all types of energy. And it is known as Planck's constant or the quantum of action. Its magnitude is 6.626 into 10 to the power minus 34 kilogram meter square per second. It is this insignificant magnitude of the quantum that makes the light of a candle or the sun appears to us to burn with constant glow. Energy quanta emitted by sources of light follow one another much rapidly and hence our eyes see light as a continuous flow. According to Planck, the average energy of an oscillator is not kT, but it was given by the expression h nu by e raised to h nu by kT minus 1. Accordingly, his radiation formula was given as like this: u nu d nu equal to 8 pi h nu cube by c cube into e raised to h nu by kt minus 1 into d nu. As an exercise, you can show that Rayleigh-Jeans formula is an approximation to Planck's formula at lower energy limit, that is when h nu is far less than kt. Also discuss what happens to radiation density at higher energy limit where h nu is far greater than kt. So now we are going to have a discussion on photoelectric effect, an important discovery of 19th century which questioned the foundations of classical mechanics. Though Planck introduced the concept of quanta in 1900, first few years of 20th century went by without getting much appreciation. In 1905, Albert Einstein published his theory of photoelectric effect. Photoelectric effect was discovered by a Russian professor, Sholtov, in 1872, in which further studies were carried out by German scientists Hertz and Lennart. Sholtov put two metallic plates inside a flask and pumped air out of it. Metal plates were connected to a battery. Naturally, there was no current through the airless space, but when the light of a mercury lamp was made to fall on one of the plates, current immediately began to flow in the electric circuit. When the light was turned off, the current stopped. He drew the proper conclusion that current carriers, which was later identified as electrons, had appeared in the flask and that they originated only when the plate was illuminated. It was quite obvious that the electrons were ejected from the illuminated metal. Another interesting observation was that for each metal there appeared to be a certain limiting wavelength or frequency nu0 of incident light. When the frequency was less than this limiting value, the electrons disappeared at once and current ceased to flow, no matter how intense the light was. It was clear that electrons were ejected from the metal because the light in some way conveys energy to the electrons in metal. The brighter the illumination, the stronger the current. According to classical physics, no matter what the wavelength of the light, the metal should be receiving the same energy. Decreasing the frequency of incident radiation, the energy diminishes and fewer electrons are ejected from the metal. But still there should be some kind of current. But experiments showed no current below a threshold frequency. Einstein regarded the photoelectric effect from a different angle. In normal conditions, no electrons can escape from a metal surface, which would suggest that electrons are bound to the metal by some kind of force. To knock them out of the metal, a little energy is needed. This energy is called the work function of the metal. Light wave has a definite wavelength of the order of a fraction of a micron, which is much larger than the size of an electron. Hence, light in the photoelectric effect behaves like its energy is concentrated in the minute volume occupied by an electron. This means that in photoelectric effect, the light behaves like a tiny particle. It strikes an electron and kicks it out of the metal. So Einstein said that light is simply a stream of quanta of energy. all the quanta of a single wavelength have exactly the same portion of energy. Later, this quanta of light energy were given the name photon. So according to Einstein, a photon carrying a small portion of energy strikes an electron with sufficient force to knock it out of the metal. On the other hand, if the photon energy is insufficient to disrupt the electron bonds in the metal, the electrons will not be knocked out and there will be no current. According to Planck's formula, the energy of a quantum is determined by its frequency, and hence it is quite obvious that the photoelectric effect has definite limits. If the frequency of the light is small, the photons do not have energy enough to dislodge the electrons from the metal. It doesn't make any difference how strong the light is, that is, whether 1000 or only 2 photons strike the metal. It must have a minimum frequency with energy at least equal to metal work function to eject a photoelectron. The situation changes if photons have sufficient energy higher than the work function of the metal. In this case, the brighter the light, the more photons enter the metal every second and greater the number of electrons ejected, thus producing a strong current. According to Einstein, the maximum kinetic energy of ejected photoelectrons are given by the expression the kinetic energy maximum equal to h nu minus h nu 0, where h nu is the energy of the incident photon and h nu 0 is the work function of the metal. Like Planck's hypothesis, this explanation also questioned the foundations of classical physics, where light is considered to be electromagnetic waves, not as particles.